derivation of mean and variance of exponential distribution from its moment generating function. How to derive mean and variance of exponential distribution from its moment generating function. That is what we're going to be looking at. But first of all, let's state the PDF of an exponential distribution. We said the PDF, which is the probability density function of an exponential distribution, is given as f of x equals lambda exponential raised to power minus lambda x, where we have this interval. It's a member of 0, infinity. That is positive infinity. That's the limit of this exponential distribution. Now, this lambda is the only parameter. So now we want to look at the moment generating function. First of all, we'll try to derive the moment generating function. Then from the moment generating function, we look for the mean and the variance. So moment generating function of exponential distribution is given by m subscript x of t equals to integral 0 to infinity exponential tx f of x dx, whereby this f of x is this distribution. Let's slot in the distribution. We're going to have a m subscript x of t equals integral infinity to 0 exponential raised to power tx multiplied by lambda exponential raised to power minus lambda x dx. You can see we already have our distribution and the moment generating function here. So the whole of this is now moment generating function of exponential distribution. Now we'll simplify this further. We evaluate. We are differentiating. We are integrating with respect to x, which means this lambda is a constant which has nothing to do with the random variable. Such we take it out and we're going to have a equals to lambda integral infinity to 0 exponential tx exponential raised to power minus lambda x dx. Now this is exponential, this is exponential. This exponential we can group it in ones since they both has the same base. And if you try to group it now, we also have x in common, which means we can also factorize x out, and this will give us a lambda integral exponential raised to power minus into bracket lambda minus t into x dx. What have we done here? Since we have minus lambda here, we now factorize negative out, and x, we factorize both negative and x, and that is why we have a lambda minus t. Now if we open this bracket here, we're going to have a minus times lambda, which is minus lambda here, minus times minus t, which is plus t here. Can we see that? Now we'll move forward. Since we have this now, we're going to introduce a bit of manipulation here so that it will be easier for us to, and again it's not even manipulation, we are going to integrate this, and when we integrate this exponential raised to power this, we're going to have a exponential raised to power minus lambda minus t divided by minus into bracket lambda minus t. That is the integration of this, and we should not forget we still have our constant here, and that will lead us to have something of this nature. I say minus lambda into bracket lambda minus t bracket close, then we have a exponential minus lambda into minus tx, then the interval, which is 0 to positive infinity. We can see we have the negative. When we integrate this is the negative here. The lambda minus t, if we integrate it with respect to x, we have lambda minus t, and that is what we have here. So we still have the same function. Exponential function does not reduce because it is a continuous function. Now we have to slot in this interval into this, and we should not forget that we have nothing to do with this right now. So therefore we are substituting infinity for x, then minus this function then is 0 for x, and we are going to have the same minus into bracket lambda divided by lambda minus t bracket close here, exponential raised to power minus lambda minus t into infinity minus exponential minus into lambda minus t 0. That is, when lambda is infinity, when x is infinity, we have this function, minus when x is 0, we have this function. The whole of this here is going to be 0 because of this infinity, and if the whole of this is equals to 0, so what will be left is minus exponential raised to power minus lambda minus t. Now, is 0 multiplied by this will also give us 0, and any value raised to power 0 will definitely give us 1. So it means this is 0 here, and here we're going to have a minus 1. Therefore, minus 1 here multiplied by this minus here, it will neutralize, and what we have left will be m sub x of t equals to lambda divided by lambda minus t, and this is the moment generated function of our exponential distribution. You can see that minus 1 that we got here multiplied by this, then what we have as final is what we have as lambda divided by lambda minus t, and that is the moment generated function of exponential distribution. Now, from this moment generated function, we need to derive our mean, and for us to get mean here, we have to differentiate this, the first order derivative, when we set t to be equals to 0. What we have here is the first derivative of moment generated function when t equals to 0 gives the mean, that is m prime subscript x of t of 0 equals to e of x. When we differentiate first order derivative and we set our t to be 0, that will give us e of x. Now let's remind us what our moment generated function is all about. So we have m sub s of t equals to lambda divided by lambda minus t. Now if we differentiate this with respect to t, we're going to have a m prime sub x of t equals to minus lambda into bracket lambda minus t raised to power minus 2 into bracket minus 1. Now, how do we get this? We can use a quotient rule or we use a product rule. If I take this up now, we're going to have lambda into bracket lambda minus t raised to power minus 1. If you have it as lambda into bracket lambda minus t raised to power minus 1, that is talking about a product rule. That is, just say lambda into bracket lambda minus t raised to power minus 1. Now we can use product rule here, and if we are not going to use product rule, we can use our quotient rule here, but the derivative will give us what we have here. Now going further, this minus 1 will neutralize this negative here, and we can avoid this raised to power 0 here by bringing down this to the denominator side, and it become positive. And what we're going to have, so this is equals to lambda divided by lambda minus t all raised to the power of 2. This is the derivative. Now we need to set t to be equals to 0. So set t equals 0. If you set t to be equals to 0, we have m prime of x of 0 equals to lambda divided by lambda minus 0 raised to the power 2, and such here the denominator is going to be lambda raised to the power 2. So the whole of this will be lambda divided by lambda divided by 2, so that we have a m prime sub x of 0 is equivalent to e of x equals to e of x equals to lambda divided by lambda raised to the power 2. And lastly, lambda will cancel one lambda here, and our final answer will be 1 over lambda. So which means the mean of exponential distribution is 1 over lambda. And how did we get this? First derivative of the moment generated function. After getting the derivative and simplify further, then we set t to be equal to 0, and that's what we have here. And the final result, we have 1 over lambda. Now we need to get the variance of an exponential distribution. First of all, let's look at what variance of an exponential variance is all about. So we have e of x raised to the power 2 minus e of x all square We've already gotten e of x, which is the mean. Now we need to get e of x raised to the power 2 in order for us to be able to get the variance of exponential distribution. So the second derivative of m sub s of t with respect to t will give us e of s squared when t is set to 0. Now the second order derivative of the moment of the first derivative, we have to get the second derivative from the first derivative, that is second order derivative from the first order derivative, and we are going to have n prime prime sub x of t equals lambda into bracket lambda minus t raised to the power 3 into bracket minus 2. This minus 2 we neutralize, or just say minus 2 multiplied by minus lambda, we have a minus 2 lambda, and we can take this to come down. Now from this integration here is supposed to be minus 3. We said so the minus lambda into bracket lambda minus t raised to the power minus 3 then into bracket minus 2. So it's supposed to be minus 3. This point here is raised to the power minus 3 if we differentiate it very well. Now if we now multiply this minus lambda multiplied by minus 2, it will give us minus 2, and by the time we take this raised to the power minus 3 down, which is what we have here, we're going to have 2 lambda divided by lambda minus t all raised to the power of 3. Now remember that we have to set our t to be equal to 0. So set t equals 0, and if we set our t to be equal to 0, we're going to have m sub x m prime prime of 0 equals to 2 lambda divided by lambda minus 0 all raised to the power of 3. If this is all raised to the power of 3 and we have 0 here, therefore we are dealing with lambda raised to the power of 3. If lambda is raised to the power of 3 here, definitely the lambda at the numerator here will cancel one of the lambda at this denominator, and at the end we're going to have 2 divided by lambda raised to the power of 2. We're going to have this 2 divided by lambda raised to the power of 2, and this 2 over lambda square is our m prime prime x of 0, which is the same thing as e of x raised to the power 2. This is what we're saying. Mx prime prime 0 equals e of x raised to the power 2, then equals to 2 divided by lambda raised to the power of 2. Now since we already have our e of x to be 1 over lambda, and we've gotten e of x squared to be 2 into bracket lambda raised to the power 2, therefore we substitute those into this equation of variance. How are we going to have this? Variance of x equals to 2 over lambda raised to the power 2 minus 1 over lambda raised to the power of 2. You can see, because we have all raised to the power 2 here, that's why we have all raised to the power 2 here, and our e of x is 1 over lambda, so everything is all raised to the power of 2. So if we open this now, we are going to have 1 over lambda raised to the power of 2. So that leads us to this. We have 2 over lambda raised to the power of 2 minus 1 over lambda raised to the power of 2. We have the same denominator here. Now simplify this further. We are just going to have 2 minus 1, which will give us 1, and since we have the same denominator, we have a 1 over lambda raised to the power of 2, and that is our variance, which means the variance of exponential distribution is equals to 1 over lambda raised to the power of 2. The mean is 1 over lambda, and the variance is 1 over lambda raised to the power of 2. That is how to derive the mean and variance of exponential distribution from its moment generating function. Thank you.